We're going to continue with the implementation of our reinsurance pricing framework. And after having discussed the sampling of the frequency and severity, we will today look into the sampling of the development pattern of claims. We will first have a look at the representation of the claim development, which is comprised of the payment pattern and the incurred pattern. And then we will have a look at the reduced representation or some statistics which are relevant for our pricing framework. And since a claim is a relatively complex object, we cannot represent all claims with all details. And this is why we use then reduced statistics. And these reduced statistics for our entire claims portfolio are shown on this screen. And we will discuss in detail what the individual items mean. Welcome back to the MeshWeaver channel. Our goal is to help you to manage and understand your data. My name is Stefan. I'm here with Roland. And today we will look into the data structure of reinsurance claims, including the development patterns. So just quickly, the overview again. What we have is a generative model, which is generating claims for the past. And then we want to use the statistics there to calibrate our model. And then we want to apply it to the future, so in a prospective manner for pricing deals. So this is more or less the overall aim. And today we are looking here, as already last time, into the generation of claims, which is more or less the same here on both sides. So at this point we don't have to differentiate, but then the calibration and the pricing, this will then be addressed down the road. So let's look again into this chart which we have here, which is showing the development of a claim where you have payments, we have development of the incurred. And as I mentioned last time already, we can define some statistics based on it and see basically which is integral over the curves in a certain way and how these integrals evolve over time. So this is the evolution of the reported lag, which is jumping from 0 to 3 at the time it's reported, and then it stays constant. We have the incurred lag, which goes up also to the level of 3, and then it comes down. It becomes even negative, which is positive in the case of incurred lags, and then it goes up again. And the paid lag is increasing, and at the end, once the claim is settled, then it remains stable. What we have is some statistics, and this is also what we can use to specify a model. So we say, what is the expected reporting lag of a portfolio? This is an input into the model. What is the expected incurred lag? What is the number of incurred adjustments we typically expect during this time? What is the paid lag? What is the number of payments which we expect? Is a claim paid at once at the end? Or are there some annual payments? So this can vary. And eventually the claim is closed. So this is also one of the statistics. We say, what is the expected closure lag? So we want to generate claims which satisfy the statistics. But all these things are interrelated. So the question is, how can we do this? The approach I choose here, of course, there's many different ways to do it, but I said the easiest for me is if I do it in a reversed manner. So I start at the end, and then I work my way to the front. So the first thing I sample is the closure lag. I have the expected value. I also define an upper limit. So basically it has to be maybe not starting at 0, because once the claim is reported, it takes at least a minimum time until you will be able to close it. So I start maybe at 2 years and say the expected value is maybe 20 years, and I say the upper limit is maybe 50 years or something like this. Yeah? So I can use a beta distribution. So I know that with these 3 parameters, it's very easy to model it. So I get sampled closure lag. The next thing I do is then to say I take a conditional reporting lag. So now I scaled my timeline, and they say, okay, the earlier I close the lag, the earlier the reporting, and the later I close it, the later the expected report. So I have conditional expectations. And by doing this, I can preserve and make sure that the overall reporting lag remains unchanged. So this is what I do for the reporting lag. And then I do the same with once I have the reporting lag and the closure lag, then I say the payments have to be within this period. So again, I scale the payment lag into these confines. So I have a conditional payment lag, which I can then sample again. And by doing this, I can preserve all the statistics for the paid lag, for the closure lag, for the reporting lag. Of course, it's very easy also to preserve the number of payments because this number does not depend on the other parameters. The more difficult is then to come up with incurred, because the incurred depends, you cannot model it independently. Yeah. So what you have to do, once you have all the payments, it's not only about the timing of the payment, it's also the amount. So you have to sample all the amounts. You have to make sure that the amount, if you aggregate it, ends up with the ultimate, which you have sampled before. So let's assume we have all the payments. So we have here these blue bars. So this defines the paid amount over time. And of course, the incurred has to be higher than this. So it's a lower bound for the incurred. So basically what I'm doing is I take an expected development of the incurred, which corresponds to the paid lag. So depending if the paid lag is negative or smaller than the reporting lag, then you have a curve which comes down. If it's positive, it increases. So I'm defining an incurred curve or reference curve, which has the incurred statistics which I want. And then I can take then the difference between this curve and the paid amount and say this is kind of expected outstanding, but I have to make sure that it's bigger than 0 because otherwise I have a problem. So there is some nonlinear operators which I have to use in between. So it's not possible to preserve the incurred lag exactly, at least not with this approach. Maybe there's other ways to do. But just to explain what I'm doing. So at the end, I can also then saying, okay, I have a expected outstanding amount conditioned on the payments. And then I am sampling the actual outstanding, and then I get my incurred. So this is the approach which I have implemented here. You can find here some technical details, but at this point it's not really relevant. But what I can then show is here the code. But what I'm then doing is represent the claims. And since I don't want to show the actual development because then it's too much information, I can do it for one claim as I did in my charts above. But if I have a whole portfolio, then the only thing what I thought makes sense if I want to show all the claims is to show the size of the claim, which is here in a log scale. So the level here tells it's a small or a large claim. And then I'm taking the statistics. You can see here the timing of the occurrence time, which is between 0 and 1, because I'm saying the cover period is 1 year. So it's between these two aqua lines here. So this is the time when the claims are expected to occur. I've also put an upper limit here for the closure. So in this case, it's 20 years plus 1, because if the claim occurs only here, then I close it after 21 years. So this is kind of upper bound for the closure length. So for each claim, as I said, I start to sample at the back. So I get the actual closure date, and I sample the reporting lag, which in this case it's a couple of years since the occurrence. And then I sample the payments, which is here this green diamond, and then the incurred, which in this case is on the positive side. But you can see in most cases it's negative, and it can be quite negative. So if the initial estimate of the ultimate is very high and then it comes down and it's very small, then of course you have a very big negative incurred lag. As a reference, I've been drawing here the expected value for each of these statistics. So the incurred is negative, and then I put plus minus half a year around because of the duration of the cover period. The same for the reporting lag, the paid lag, and the closure lag. So this is how I represent the claims to get an idea, but of course I'm also interested in the statistics. But now the important part is down here. So as I already mentioned earlier, we can define a conditional reporting lag. So given the closure, I can then define the conditional reporting lag by scaling the timeline. But if I do this for all the claims, I should more or less end up again with what we are expecting. This is exactly what's happening. So the input is 2.5 years, and for the condition I get 2.506. Very good. The same with the conditional incurred lag. I also say I have minus 1.5, and if I scale it in different ways and then I aggregate it, I get minus 1.513. So it's also very close. Same for the paid lag, again conditional, it's again almost perfect agreement. Then the reporting lag as well, I defined the input of 2.5, I get 2498, so I think this is good. But then, if I look then to the incurred lag itself, which is then after having these nonlinear operations, then the actual incurred lag is minus 3 years instead of minus 1.5. So this is not possible to, or at least with this approach, I cannot directly reproduce the input. But for the other statistics, you can see again the paid lag, it's 5.18 instead of 5. The closure lag, I mean, there is no conditional, I've simply specified the parameter with a maximum of 20, and I get 10.02. Last two statistics are the number of incurred adjustments. So I entered 5 as an expected value, I get 5.003. And for the number of payments, the input is 10, and I get 10.01. So you see this model is able to reproduce the input statistics or the parameters, so the statistics are more or less identical to the parameter. Of course, I had a relatively large number of samples. You can see here it's 100,000, so it's not 10 or 20 or 100 claims, it's a large number, but just to show that the approach is actually working. So this is the kind of model which I use to generate claims. Now, so far we've only talked about the statistics, but of course what matters at the end of the day is then the actual payments. So I didn't enter a payment pattern. So I'm just using the sampling and the beta sampling. So this is, we have then to find out if the payment pattern which results from this approach, if this is kind of reasonable or not. Of course, I can control it by the number of payments, which is one of the parameters which I'm entering. And so this is more or less what I have accomplished so far in my claims generator or the generative model. And if you think that this is kind of reasonable, I mean, you've also started to implement some loss models. And the question is this basically what we use now to move forward? Or do you see any other features which should be implemented in the generation of claims?
I mean, when I look at what's state of the art, what do people do? They take some average payment time or some average settlement time or whatever, and then they say, oh, what can I do with one parameter? And then they take a Poisson distribution, and that's it, right? So I would say this covers like 90% of the cases. Of course, you can take reserving patterns, but I think they have also always a bit of a political notion. So I'm not sure how good they actually represent. And you see, so you have one free parameter, so we can use the free parameter to again calibrate something like an average settlement time or an average time to incurred or whatever.
That is exactly what we do at the moment. This is the parameters which you mentioned is exactly the average settlement time.
And so I think this is by far better than just saying, oh, let's take a Poisson distribution because it's the only thing I know. Definitely also what we have to consider is how much of a primary effect is it, right? Because this is, it will it will determine discounting.
Exactly.
But discounting is a secondary effect, in my opinion. So anyway, we are kind of second order optimization already.
Yeah. I mean, the payment they have two roles. One is, as you already mentioned, it's how to calculate the present value. And this is also something where we need to understand that if you look at the model, we have separated frequency, severity, and the development. But if we say at the end the premium rate and the loss ratio, they determine the present value of the claims. Yeah? So somehow all three components interact. So it's the frequency times severity times the discount factor.
Yes.
And if I say yes, I believe in the rating of the ceding company, and that the premium rate and the average loss ratio is more or less one constraint, then I need to make sure that these three parts are aligned. So I cannot model them independently. Of course, I can say I don't believe the client, so I just put in my own parameters, then I calibrate it, and then I don't need it. But this is exactly one part. But the second part, from a reinsurance perspective, quite often, especially in long tail business, you have so-called index clauses. So where the payments also not only determine the discount, but they also determine how is the claim split between the insured and the reinsured. It's not only having a limit and the deductible, but you first take a given index to discount the claims, and then you apply the layer conditions, and then this is how the claims are split. So this is an additional effect which you need to consider. But quite often, at least in my time, when I ask the people or the underwriters, I mean, if I have a payment pattern, it can mean two extreme things. The reality is in between. Either it tells me what is the probability that the claim is paid at one particular year, or the other extreme, it says I'm making multiple payments, and it tells me what is the portion of the claim which is paid in every year, right? And this, of course, if you have things like index clauses, then this is a completely different effect. And nobody was able to tell me what the payment patterns which they're using, what they actually mean.
But you see, so if you want to go down the rabbit hole of index clause, then the best, in my opinion, the most complex thing that you have to model there is not even the lag, but you have to model any kind of inflation assumption.
Yeah.
And I've modeled a lot of things in my life, and from everything I've ever tried to model inflation, and especially this kind of inflation, which is claims inflation, which is normally completely different from any kind of CPI measured inflation. In my opinion, it's very, very difficult to model this. And so especially when I still did this pricing many years ago, this was always a bit hand-woven, right? And then I spent actually quite some time modeling economic scenarios, and there we tried at least to make an assumption about CPI and this kind of inflation, but it was so difficult. And I really think inflation, also when you look at financial markets, you cannot buy any product that hedges you against inflation, and there is a reason why. So I think we'd have to really also speak about how we want to model inflation to take this into account.
But I didn't want to go this far, but of course it's a very important point. The claim inflation is one of the most relevant uncertainties we have in the model. But for me, it was only how to apply an index clause where the index is given.
Yes,
yeah?
Yes.
And so you don't... Maybe it's just a proxy for the inflation, but it just tells you, the index clause, how to split the claims. And as I'm trying to explain, it's none of the actuaries or the underwriters I asked was able to tell me what is the meaning of this payment pattern you are using.
Yes.
Does it reflect the probability for paying a claim in the first or second or the third year? Or is it you have partial payments and you split the payments over the whole period? Of course, probably it's a combination of the two. So what we did is then to say we take one extreme and we take the other extreme, and then we kind of blend these two approaches.
Yes. But I think most people really define it via the triangle, right? And so you just shoehorn everything you have into some triangle, and then you look at this triangle and finish.
But
so
the
I
triangle tells you something about the whole portfolio, not about the individual claim. Yes,
of course.
That's the challenge.
But I think this is still like state of the art, even though the art is not brilliant in this case.
Yeah.
So give us your comments. So what do you do? Do you use triangles? Do you do something more sophisticated? Are you capable of defining what these patterns really mean or what they should mean? Leave us a comment below and we are very happy to take up the discussion.
So with this, I think we can close today's session, right? Thank you for staying with us and don't forget to subscribe and to like us. And we see you again. Happy weaving.